Hello, F Sharp. Welcome back. We are now in the second part in our series on optimizing a topological sort algorithm. In this case, the particular one we are using is Kahn's algorithm. And I am super excited about this. The last time what we did is we implemented a naive version of Kahn's algorithm. And what I mean by that is we took the version of it that was described on Wikipedia and we translated that as closely as we could to an F-sharp version using immutable data structures and recursion. So it's a very functional programming approach to implementing that algorithm. And then we benchmarked that. And the reason we wanted to do that is we wanted to establish a baseline for how fast are we. Now, in our case, how fast do we want to go? What's our ultimate goal? What are we trying to achieve? Well, in our case, this algorithm is at the heart of some simulation code in one of our products. And that simulation code performs many iterations inside of it. We need to be able to perform 1 million iterations, and we would like to be able to do it in 1 second. And that means we have 1 microsecond of time budget per iteration. And this piece of code runs every single time. It is absolutely the hottest piece of code in the entire simulation. Once we get the sort, we do some other work. We update some values as the simulation is evolving, but this is by far the most important piece. So 1 microsecond per iteration. Whew, that's fast. Now we will accept taking up to 10 seconds for a full simulation of 1 million iterations. That means we have 10 microseconds per iteration. Still pretty fast. Our goal is our aspiration. We know we are done when we can get this benchmark down to 500 microseconds. If we get this thing down to 500 microseconds, that means we're able to perform a topological sort in 500 nanoseconds. Because what this benchmark is solving 1,000 random graphs of the size that we are interested in. And the baseline performance we have right now is 60 milliseconds. So that's about 100x off where we need to go. But it's great that we now have something to improve. It's much easier to improve code that we know is correct than to try to get fast code that's wrong. So I always like to write the naive version first, make sure it's working correctly, and then benchmark and see how far off I am. Right now I'm 100x off. So what do we do at this point? Well, the next step that I take is I like to go profile this. And the way profiling works in this code is, since last time I actually started, I decided to add the argue library, which is a fantastic F-sharp library for doing command line arguments and parsing. And I have 2 different tasks in it. So when I call this code, I could say, I want you to run the benchmarks, or I could say, hey, I want you to profile. And if it's going to profile, I ask for which method am I wanting to profile and how many iterations. And what this does is it runs the exact same code as the benchmark, but it just runs it over and over and over and over again. And that way the profiler is able to look at what real world performance would be. And so we can say like, hey, where are the slow parts of our code? Now, the profiling application that I'm going to use for this is .trace, which is a product from JetBrains. I pay for it out of my own pocket. I get no support from any company for any of the products that I use. I buy them all myself. And I just think it's a fantastic product. So I highly recommend it. Another one that I really like is Superluminal. It's also fantastic, but .trace is a better one for what I'm wanting to demonstrate today. And so I actually already have that loaded up. And if you want to know all the ins and outs of this tool, I really recommend you check out their documentation, and they have some great videos where they go in to describe what all these different settings are. What I'm going to use is the profiling type I'm going to use is sampling. Now what this does is it just takes snapshots of the call stack periodically. And what it's assuming is like, hey, if I take a snapshot, slow code has a higher probability of showing up in the stack trace than fast code, because fast code, it'll go in and it'll come out really quickly. And so you won't necessarily see many snapshots of it. So the idea here is we're going to take a lot of different snapshots as this thing is running, and whatever shows up a lot, that's what's probably slow. So I am just showing the configuration options for this, where this is just the path. And let me expand this a little bit for you just so you can see this a little bit more clearly. So I gave it the path to where when I build this thing in release mode, where the executable ends up, and say like, hey, this is the executable that I want. And then I'm giving it the command line arguments that I want it to use. So in this case, I'm saying, hey, the task is to profile. The method I want you to profile is a version 1, and I want you to perform 500 iterations of that method. Great. So then when I say go ahead and start, what it does is it goes ahead and starts up the code, and it's going to give us a little bit of a visualization of what the resource usage is. And just with this, we can quickly identify some things. In this case, we're not seeing it, but if, like, for example, if the memory was really choppy, like a saw pattern, we know we would have lots of allocations and deallocations. That's not, well, approximately. that's not quite correct, but we would be able to see if our application is like consuming a lot of memory and then dropping a lot of memory and consuming a lot. We also saw there that that yellow area was the CPU usage, and right now it's just flat out the entire time. So that's not a lot of information. That's not a lot of useful information for us for this purposes, but that can possibly be helpful for some people. So now I'm going to walk you through a little bit about what we're seeing. Here on the left is a place to visualize call stacks. You kind of visualize where your application is spending code. And it's telling you here, like, hey, I'm spending 93% of my code in main, and then 90% profile, 90% in V1, and then the sort, and then da-da-da. So you can kind of get an idea quickly of what are the hot methods here. When I click on piece of code on the right, and this is really nice, it'll show you the source code that corresponds to that. So you can quickly go in here and say like, hey, you know, what is this hot piece of code? And it will show you what it is on the right. You can even look at the IL version of it. So this can be really helpful to figure out exactly what IL is being generated. We're not going to use it here today, but I just want to point out, oh, no. Yeah, okay, this is kind of like my apologies. So this is kind of like the C# version of this. You can also say like, hey, I want you to interpolate the IL so I can see what's going on. So this can be useful to kind of get an idea of exactly what's going on. For us, this is what we want to see. And then here on the bottom, we get an idea of what subsystems our code is using the most. And so we can see like, hey, it's the set tree module. So this is the code around managing sets in F#. We also have, can't quite see it here, but I'm just going to cast helpers, language primitives. So this is up here is just a visualization. And then here's kind of just a tree where you can kind of zoom in and say like, hey, where are you spending the most time? Now, okay, again, if you want a much better dig into all this tool can do, I recommend checking out JetBrains. What we're going to do here is we're going to see something pretty obvious pretty quick. As we start breaking into our code and seeing what's taking the most time, and we can say like main, we expect that. Profile, we expect that. That's the function we're calling. V1, again, expected. It's calling the sort. Again, that's all that this method is doing. And let me come back to show you that I'm not just making stuff up. So what it is calling is this piece of code here, this method, it's just calling this repeatedly. And what it does is it's just looping through all the graphs, and it's calling this sort function. So the fact that we're seeing sort show up a bunch here, again, that's what we expect. Inside of sort, though, we see something interesting. we see it's spending 50% of its time on the decompose function and 28% of the time on the loop. Okay, well, let's look at the code and see what the heck is going on. So I'm going to go ahead and come all the way down here. So this is the call to sort. It has some helper functions in here, which are the loops for actually doing the logic. And it's saying it's spending 50% of its time here on this graph decompose function. What the heck? Well, let's look at how we've modeled our domain. And some of you may have already seen, like, Matthew, this is completely obvious that this is a terrible idea. Well, I wanted to show you all the process I go through instead of just glossing over some details and things that are obvious, because they're not obvious to someone who's just starting out. So what problem are we running into? Let me just zoom in a little bit. Right now, we modeled graph as just a list of edges. Okay, well, that's a fine way, and that's a valid way to model a graph. It's just, hey, it's just all the edges. The problem is that the Kahn's algorithm really relies on understanding, sorry, let me unpack these a little bit. It really needs to know the sources and targets of nodes. So we've modeled a graph as a list of edges, but the way the Kahn's algorithm thinks about it is it wants to know, hey, for a given node, I need to know what edges are coming out, and I need to know what edges are coming in. And so it's constantly, so that's the way it wants to work. But we gave it a list of edges to start out with. And so the very first thing it has to do is it has to do all this rearranging so it's able to look up which edges correspond to a node. And so all that work up front, before it can actually do the sort itself, it has to create these maps for being able to look that information up. And apparently it's taking 50% of the time. Now, there is no restriction. There's no restriction in the problem I'm dealing with to say, like, hey, you have to model a graph as a list of edges. You just don't. I just happen to choose that as the naive thing to do. And what's great is now in profiling, we're saying, like, maybe that's not a great way to do this. So great. Based off of this, saying, like, hey, is there anything we can do to kind of get rid of this decompose step? Well, what we could do is, instead of modeling a graph as a list of edges, let's model a graph as the thing that we want. So I'm going to come here to version 2, and I'm going to put version 1 up. I'm going to put it over here. Come on, version 2. I'm going to put version 2 on the right so we can kind of compare and contrast these. So version 1 on the left, version 2 on the right. Version 1 says a graph is a list of edges. Version 2 says, no. A graph is 2 maps. One map is for the sources of a given node. And sources are the edges that are coming into, are pointing at the node. The targets are the edges leaving the node. So for a given node, like all the different edges that are coming off, those are the targets. It's what the node is pointing at. And we're saying, hey, no, we're going to model the graph this way. And this way of modeling a graph is much friendlier to how the Kahn's algorithm wants to work. So because we are in complete control of our domain, we might as well do ourselves a favor and model things in the way that the algorithms want to think. And this is one of the most important things for me that I've been learning and working on the last couple of years when it comes to writing high performance code. It is okay to have completely different domains for different purposes. Again, some of you may be saying, Matthew, that's completely obvious. It wasn't obvious to me. I typically wanted to create a single domain and do everything in that domain. What I've evolved into now is where I will have a domain representation that is ideal for the modeler. So the person writing models. There is the domain that they work in, and it's very streamlined for what they do. I then take that representation and then transform it into the simulation domain, or the domain, a representation that is ideal for the computation side of the problem. And so this is an example of where, like, hey, on the left may have been a fine way to model things from a modeler analyst point of view, but on the right, we've created a version that is more friendly for the computation point of view. So let's now look at what the performance of this is. And you're actually going to see, let me go ahead and close this. The code in version 2 is not that dramatically different. The main thing that has changed is that the code for creating a graph has changed a little bit. Instead of having a decompose function, we're actually pre-computing those sources and targets maps. And the way that changes our code here for our benchmarking purposes, when we generate the data in version 2, we're using the same random number generating seed. We generate the same edges, but instead of graph being just a list of edges, we're going to say, hey, go ahead and compute the graph. So in this case, it's pre-computing those maps that we are going to need. And then when I come down here to the benchmark for version 2 does not change significantly at all. It's the graphs in version 1 are equivalent to the graphs in version 2. The only difference is in how they are arranged. So when we run this benchmark, we get some very different results. So version 1 was taking 60 milliseconds. We're now taking 36 milliseconds. We've almost halved the amount of time the Kahn's algorithm takes. And that makes sense. Because again, if you come back here, hey, this decompose, we've basically moved that work into the domain representation. And so we would expect an approximately 50% improvement in speed. And that is absolutely what we're seeing. Great. Fantastic. Well, let's go a little bit farther. Let's see what happens when we profile version 2. Where has the bottleneck moved? And so I'm going to come in here to .trace. I'm going to change this to method 2. And I'm going to say, go ahead and sample. And this will run a little bit faster because I haven't changed the number of iterations. It's still 500, but now we are profiling that second method. And so what we are expecting to see is that the decompose function disappears because it's no longer a part of the logic, and something else has now become the bottleneck for the system. And that's what we want to identify and improve in this next iteration. And we're loading up our data so we can see what is taking all the time. So what is slow? Again, for me, step 1 is I usually just start expanding this tree out to see like, hey, what's taking the time? And okay, we're seeing some different stuff. Notice decompose is no longer here, which we expect. It's no longer even a part of the logic. And we're saying, hey, loop is now taking 43%. Invoke, so this is it calling an anonymous function. Is what's going on here. Another invoke. And generic compare. So what am I seeing here? I am looking for methods I wouldn't expect to see, or I'm looking for methods that are taking a lot of time or repeated. And that's actually what I actually like to do is I like to come up here to this method up here. So this is the top level thing for me. And then I come down and look at, for that method, what are the main subsystems that I am spending my time in? And I can go ahead and, so system code is the big one. And it's spending a lot of time in the set tree module. Again, that is the code around managing trees in F#. So updating, inserts, removes, that type of thing. Spending a lot of time with the tree module, creating the trees, adding to the tree, removing elements from the tree. We got some compares. So this is what it's using for generic comparison. And this is used extensively in the set modules in F# and in the map module. And you actually see the map tree module down here as well. So there's not a single function necessarily that's dominating, but what we're seeing is like, man, we are spending a lot of time managing sets and managing maps. And that seems to be really dominating our runtime, which if we look at our domain, makes a lot of sense. Let's go back to version 2 and see how we've modeled this domain. Well, we've said a graph is made up of 2 maps where the key is a node and then the value is a list of edges. And down here, sorry for the jumpiness, we are using remaining edges is a set. All right, remaining edges is a set of edges, and we're constantly updating that. And so what's happening, the way this algorithm is working, is that we have maps for looking up the edges we're interested in, and we have a set of edges that we are slowly removing values from as the Kahn's algorithm progresses. So a lot of work looking things up in map and a lot of work in updating sets. Okay, is there anything that we can do to improve this? So the first lesson should be, hey, can we move computation to where it's not going to impact us? And that was the idea of taking decompose and basically moving the decomposed logic into our domain representation. So we don't even need to do that work. So get rid of work you don't even need to do. Second thing is there a data structure that's better suited to my purposes? So maps and sets in F# are AVL trees. And I think there's a slight variation on an AVL tree, but they're a tree structure. They're a balanced tree structure, which means every lookup is log n. And when you do that a lot, that adds up. So the question is, hey, is there a key value collection that has a faster lookup speed than map? And the answer is dictionary. Well, I really like the immutability. Well, I like the safety of F#'s map because I know if I try to change it, I'm just going to get a new map. I'm not going to have things changing out from underneath me. Well, fortunately, there's a thing called the read-only dictionary. And that means you get the speed of dictionary lookups, but you know that the stuff isn't going to change out from underneath you. So how about what we do is instead of using maps, we're going to use read-only dictionaries, and we're still going to have that nice safety. The other thing that we're going to use is instead of, let's see where I have this. Instead of using a set for keeping track of what edges are remaining, we're going to use a hash set. Okay, well, that's not an immutable collection and it's something that you're modifying all the time. Is that really okay? Yes, that's okay. We're stylistically, for me, mutation is a tool. I think of mutation is a tool, and sometimes it's the right tool to use. Where I try to be very disciplined with it, though, is mutation should not escape its context. And so if the mutation, in my case, if the mutation stays within this sort function and doesn't escape it, it's all good. It's the moment that mutation escapes boundaries that things get really ugly and really dicey. Now, sometimes that might be necessary for performance reasons, but for me, the ideal is I'm okay with using a mutable collection as long as that mutable collection, that mutation is isolated to a particular area. And so the main difference we're going to use here is instead of remaining edges being a set, remaining edges is going to be a hash set. And that means we're not going to need to recreate sets all the time. So we have this new version. We're going to use hash set instead of sets. We're going to use read-only dictionaries instead of maps. And if we come back here to the code looks exactly the same. And the logic for creating the graphs is exactly the same. The only difference is instead of turning it into a map at the end, we're turning it into read-only dictionaries. And so when we benchmark this, we're going to see an improvement. Another huge jump. I'm just zooming in to make that. Oh, look. There we go. So now we're at 9 milliseconds to solve 1,000 graphs. So this has been a huge performance improvement. First step is we moved work to a better spot. We no longer have to do decompose. We've just baked that into our domain representation. Second step is, hey, let's identify some collections that are better suited for our purposes. Okay, well, this is fantastic. This is a huge improvement, but you know what? We got a long way to go. we're still over a little 10x from where we want to be, but we have made huge improvements. And so that's all I want to cover for this week. But let me tell you, like, we got 10 versions of this thing. So we're not even a third of the way through. So there's some exciting stuff coming up. I hope you enjoyed this. I hope this was informative. If you have any questions, please feel free to comment on the video or hit me up on Twitter. I love answering them and I love doing this. So I hope you guys have a wonderful day and thank you so much for spending some time with me. Thank you. Bye-bye.